Oh, let's try again. Good morning.
Good morning.
All right, there we go. Thank you. Welcome to the first panel, the first item of the day. My name's Bill Klepsch, and I am the Cenic Board Chair. And I welcome you all. You have come to what my dad used to call it, you're here with the heavy hitters this morning. And I think you're really going to enjoy this panel. We have 3 speakers who are just a delight. I've been asked to remind all of you that after this session, if you want to, you can stop by the registration desk and pick up a beautiful internet map, suitable for framing. It's Cenic's gift to all of you. So I'm going to go ahead and introduce all 3 of these gentlemen, and then we will have each one speak for about 20 minutes or so, and then we'll do a Q&A on each one. The subjects are quite different, even though they're all very interesting. Up first is Harvey Newman. He's been a professor of physics at Caltech since 1982. In 73-74, he co-led the team that discovered the 4th quark flavor known as charm. Since 1994, has been a member of the CMS that discovered the Higgs Boson at the LHC in 2012. Newman has had a leading role in originating, developing, and operating state-of-the-art international networks and collaborative systems serving the high-energy and nuclear physics communities. As of 2015, he and his Caltech team and partners have begun the development of the architecture and methodology for the use of exascale computing facilities for high-energy physics and other data-intensive science areas. He is currently developing the next generation of software-defined global networks together with ESnet, Internet 2, Cenic, Starlight, SurfNet, and many other leading network partners, as well as key programs such as our very own PRP. Speaking next will be John Delaney. John Delaney is professor of oceanography at the University of Washington. Since 1997, he has directed development of the Regional Cabled Ocean Observatory in the Northeast Pacific Ocean as part of the NSF's Ocean Observatories Initiative. This distributed remote sensor robotic network will convert a sector of the Juan de Fuca tectonic plate and overlying ocean into an internationally accessible, interactive, real-time national laboratory capable of reaching millions of users via the internet. Such networks are at the leading edge of ocean and earth science research and education. Delaney, who joined the University of Washington faculty in 1977, has published nearly 100 scientific papers and articles and has served as chief scientist on more than 45 oceanographic research cruises. Speaking to us finally will be Greg Bell. Greg is the CEO of Broala, known to many of us as Bro, a network monitoring and cybersecurity startup based in Berkeley. Prior to that, Greg was the director of the Scientific Networking Division at Lawrence Berkeley Lab and director of the Energy Sciences Network, fondly known as ESnet. ESnet is the U.S. Department of Energy's high-performance backbone and a close partner with Cenic and on the Pacific Research Platform Project and other initiatives such as security. Previously, Bell served as chief technology architect in Berkeley's Labs IT division. His professional interests include cybersecurity models for high-performance environments, advanced networking technologies, and data-intensive discovery. That's the intro, so I'm going to ask Harvey to go ahead and come up now.
First of all, thank you for the chance to talk to you today. And what I'll be talking about is a bit about the science, in particular high-energy physics, some of the challenges that we face, how we engage with the technologies to solve some of our problems, and also we hope to develop solutions that are applicable to many fields of data-intensive science. So what you can see here is a sort of collage of some of the scenes from high-energy physics on the left, future sky surveys such as LSST and shortly after the Square Kilometer Array, which have similar but at the same time somewhat qualitatively different challenges. And in the future also, perhaps the dominant application compared to high-energy physics and the other areas is genomics. What we have just done in the recent years is we've completed the first run at the Large Hadron Collider, where the major result, among many others, was the discovery of the Higgs boson in 2012. We're now engaged in moving beyond what we understand in the Standard Model, searching for what is certainly the more fundamental theory which existed in the early universe and underlies the Standard Model and all of physics. I'll talk about some of our developments to help meet the challenges, and then at the end I'll turn to the new application to use the emerging generation of exascale computing systems both to satisfy our otherwise overwhelming computing power needs and also to serve data-intensive science. So I'll be talking about new windows on the universe and also about our future in terms of networks and computing. So this is a one-slide summary of what we understand in the Standard Model, a beautifully simple picture of families of quarks. There are 3 families of quarks, each containing 2 quarks, and also 3 families of leptons. The first family is what composes normal matter. In high-energy physics, over the last century, 35 Nobel Prizes have been awarded for the experimental discoveries and theoretical breakthroughs. And it's actually been amazing in the 21st century how Nobel Prizes have been awarded in 2007 for the discovery of our accelerating universe, the fact that there is dark energy which is accelerating the far reaches of our observable universe. In 2013, for the Higgs boson, the theoretical ideas underlying the experimental discovery. In 2015, what's called neutrino oscillations, how when neutrinos travel long distances, they change their type from one family to another. The Standard Model, as powerful as it is in its predictive power, has a number of shortcomings. Apart from the fact that, as I mentioned, it doesn't work at all in the universe, it doesn't explain the existence of dark matter, which we already know through observing rotation curves of galaxies and galaxy clusters dominates matter in our universe. It doesn't tell you anything about the pattern of particle masses. It doesn't have unified forces in the early universe. And it doesn't say anything much about dark energy. So this is a very beautiful, simple picture, but there are many questions unanswered. And so this is a snapshot in 2012 of announcing the Higgs discovery. In 2012, in the middle, you see Higgs and Englert, who jointly discovered the underlying theoretical ideas leading to the 2013 Nobel Prize. And you can see the impact on society, which is our engagement with fundamental questions also has universal recognition and also excites young people, gets them into science in the first place, and that in itself is a very important outcome. Highly reliable advanced networks, high-capacity networks have been an essential element of this success. Every PhD which has been awarded in high-energy physics for the last many years has relied on such networks, and that will be so also in the present investigations. But we're facing new challenges in terms of the scale, complexity, and scope of what we do. To appreciate the complexity, you can see immediately if you look, here is a picture of some collisions from the Large Hadron Collider. You see a portion of the ring on the left. In the middle, you can see that as we progressed in terms of the intensity of the machine, every time the bunches of protons cross, we got more and more interactions, dealing to an incredible increase in the complexity that we have to deal with, an increase also in computing power and storage required. So moving beyond the Standard Model, the higher energy of the LHC in the present second run is bringing with it greater opportunity for discoveries, but greater technical challenges. In the future, as we move on, we're currently in the second run, where the number of interactions per crossing will reach more than 40. As we move forward to the high luminosity LHC, a second major phase that will be implemented in the next decade, this picture will become extremely dense, where the number of interactions will probably reach 200. So talking about the challenge of scale, we currently have 300 petabytes under management among the experiments. During the course of Run 2, we expect this to increase to an exabyte. In the future, the data sets will grow by another factor of order 100 to the 50 to 100 exabyte range by the time the high luminosity LHC starts around 2025 or 6. So our reliance on networks will only increase, and it will take new ideas and new concepts in order to manage this data, its global distribution, how scientists throughout the world are able to access the data, analyze it, and produce results. This is the core of our networking. On the left, you see what's called the LHC optical private network, a sort of misnomer. It's a star network that connects CERN to the major centers. The global ensemble of centers includes 12 national scale centers, 160 centers of smaller size, which are hosted at universities and smaller laboratories, and about 300 clusters which serve individual physics groups. As the smaller facilities and the use of these facilities for analysis throughout the world rose, then another paradigm was needed to serve this level of the overall picture. In the middle, you have what's called LHC1, which stands for the LHC Open Network Environment, and it's become so complex you can hardly see all the links interlinking both the United States, Europe, and Asia in a global ensemble, a sort of peering fabric, a virtual routing and forwarding fabric, which spans the world regions. You can also see the major continental and transoceanic infrastructures, Internet 2 and ESnet, and also GEON, the pan-European network, which serves many disciplines, but also in particular high-energy physics. The rise of data is shown here. This is just during Run 1, from the startup in 2009 to 2014. For just one experiment, the Atlas experiment, you can see in the histogram month by month how the flows to various sites have increased, reaching a peak of 112 gigabits a second, 170 petabytes transferred during 2012. By that time, the so-called Tier 2 centers, the ones at the universities and small laboratories, were already able to more than saturate 10 gigabit per second links in 2012. The overall flows for our competing experiment, my competing experiment Atlas, and my own is CMS, the typical flows grew to 8 to 10 gigabytes a second. And CMS, my experiment, has changed its paradigm in a way I'll explain, so that our flows, which were somewhat smaller, are now equal or greater. And as you can see, the rate of growth is also impressive, and I'm sure that also Greg will say something about the recent rapid exponential increase. Part of the driver is certainly the science need, partly is technical capability. At the very advent of the present generation of 100 gig networks, before there were 100 gig transoceanic networks, the first research link, 2 days after the first one, which was implemented across the Atlantic, were able to generate large flows from our production systems. So we had 20 gigabits a second between Caltech and the facility in Italy alone, 27 gigabits per second overall. Since that time, typical flows have sometimes reached the range of 40 gigabits a second. And there was one incident last September when the Wisconsin site generated a flow of 92 gigabits a second. So all the links to the Tier 2 centers in the US are shown there, generally at the 100 gig level. So the move to 100 gigabit networks was very timely and welcome and matched to the needs, but wasn't, let's say, much more than was needed. So I just wanted to capture some of the recent developments. This shows, I think we've seen this before, the ESnet extension to Europe. This succeeded the transatlantic network before it, which I co-managed, called US LHCnet. And this was a very important development with 300 gig links across the Atlantic, plus 40 gigs, a total of 340 gigs to Europe. This also provides major connections to the US laboratories at Brookhaven National Lab and at Fermilab. And you've seen this before because this is a global enterprise, and so this is a very important development. The first 100 gig link between Tokyo and Seattle coming into service in the next couple of weeks. And as you heard from Dave Reese, this is just the leading edge of a major increase in connectivity between the West Coast, Pacific Wave, onward to Starlight and across to Europe, and the Asia-Pacific region. And in order to make this a global enterprise, one of the key points is Starlight, originated as StarTAP by Tom DeFanti, Maxine Brown, and others working with Joe Manfredi. Joe Manfredi now leads the Starlight facility, and as shown here, it now has 34 individual 100 gig wide area network paths. Last November, we cooperated with Joe as one of 1,500 gig demos that were done then. In terms of the scale, the traffic, as one example on ESnet, has expanded exponentially with remarkable regularity since 1992. The average is about 72% per year, which is equivalent to 10 times every 4 years. And this trend continues. In February, there were 41.5 petabytes sent into ESnet, accepted by ESnet just during that month. And the projection is 100 petabytes per month by this December. Looking at the traffic, there's a very nice portal you can visit, my.es.net. And when I took this snapshot, there were typical flows, aggregate rates of 150 to 200 gigabits a second, and peaks to 300. A lot of this is, not all of it, but a lot of it is high-energy physics traffic, and also goes to show that although the networks are capable of handling this and supporting our science program, the amount of headroom is not tremendous. If you look at the weather map, you can see there are some links in the orange and red, especially to Fermilab in Brookhaven and across the Atlantic. Well, I think you can already foresee, thinking ahead, that the projection of this would provide a firm justification for the next generation of ESnet in about 3 to 4 years from now. Now, the other challenge is complexity. So here is a snapshot of LHC workflow for the major experiments. What you can see on the left are the transfer throughputs, which are typically up to 20 gigabytes a second with peaks to 35 gigabytes a second. What's going on are multi-terabyte data transfers from hundreds of sources and sinks. There are transfers of from 12 to 30 million job output files a day, and the physicists are accessing tens of millions of object collections a day. And some of the systems, one called AAA, which stands for Any Data, Anytime, Anywhere, maintains more than 100,000 open network connections at once. Now, another aspect of the complexity is the change in the model. When I first conceived of this worldwide system in 1999, it was a very orderly, hierarchical system. As I mentioned, the national centers, the smaller centers, the individual clusters, in a hierarchical sort of architecture, which you see in a cartoon on the left. And this has migrated to more of a concept of what's called a cloud model, where the emphasis is on scientists accessing, processing, and then further distributing data from any source, essentially. And so what has come with this is that now there are flows which go among many sites, and a new kind of protocol based on something called XTRU-D that finds data at any site and can access and transport it. You see the rising tide of these flows, which now have sometimes reached the same level as the organized data transfer. Also using our pervasive monitoring system, which is able to keep up with this. So this is what's called the LHC open network environment. In a way, you can see it a bit better. The first impression is extreme complexity. It's a major achievement of the world's research and education networks that have mobilized on our behalf to support our science program as a leading edge program, paving the way for others, and interconnecting regions with this virtual routing and forwarding fabric. Well, so that's a great news, but the other thing, the challenge is, it's a system with limited complexity. And we don't know how it would scale really or whether it can be replicated as a general solution. So it leads you to think more about the next generation. The traffic on this fabric grew by nearly 90% just in the last 12 months. Finally, another source of complexity is the diversity of resources. In addition to our dedicated resources, we sometimes get opportunistic allocations of resources. For example, there was a major one at UCSD in recent months. But also, we've generalized this to also use cloud services to the extent that's possible. And also in the future, as I'll say more about leadership class and eventually exascale computing facilities. What you can see on the right here is an example where about a quarter of our total production was carried on the cloud as of last month. Projecting forward, this is a study which was done a couple of years ago by Eli Dart, who's here, and Bill Johnston. If you project forward, you see, first of all, that the traffic, which is projected from requirement studies, will follow pretty much the historical trend, a factor of 10 every 4 years, if not a bit higher. And also, if you look in detail, you see it's not only high-energy physics, but other fields that will have similar needs, rising to an exabyte per month by about 2020, and 10 exabytes per month by about 2024. So another message is that high-energy physics traffic, as it grows, will also compete with traffic from other disciplines, from basic energy sciences, biological and environmental research, and advanced scientific computing. Another class of projects which is rising are the major astrophysical sky surveys, such as LSST, which should have first light in 2020, and the Square Kilometer Array, which will start shortly after and continue into the 2030s. The real-time aspect of this project, shows a picture of the camera, a 3.2 gigapixel camera, which is being developed at Stanford National Accelerator Lab and Harvard, for example. And you see also the telescope, which will be situated in Chile, but in fact, the connectivity between the United States and major centers such as NCSA will go via Brazil, via Miami, and then to Brazil, and AmLite, Heidi is here, has been deeply involved in AmLite. The real-time aspect. So I think Larry Smarr mentioned already that one of the operational modes of the LSST facility is to take high-resolution images and distribute them very rapidly in seconds, millions of such images per night, so that other telescope facilities can also focus on emerging cosmic events, and the events as they emerge can be studied in detail. SKA involves 3,000 antennae of different types, covering more than 1 million square kilometers in Australia and Africa. And from the high-energy physics point of view, it looks to us like an enormous data acquisition system where 15,000 terabits a second will travel. It's not so much more than in our experiments, but for us it's tens of meters. And for them, they have to transfer the data over hundreds of kilometers. And this just shows some of the impressive science program of SKA that will sort of drive these needs. Finally, in the next decade, there's a question raised by people who work in genomics about whether the dominant applications will be, as they say, this is their words, astronomical or genomical, if that's a word. And laying out what will happen, it depends upon how much human beings will get into measuring their own genomes and looking for signs and the patterns that show the way to either emerging diseases which are likely to happen, or different level of sensitivity to drugs, or other characteristics related to how you deal with disease and treatment. If you imagine that somewhere between 100 million and 2 billion humans will have their genome sequenced, and also realize that because there are errors and variations, you have to do it 30 times, you get these enormous numbers, both in terms of data flows. There'll be a number of flows which are foreseen of 10 terabytes per second. storing a comparable amount to the high luminosity LHC, perhaps a bit more. For us, 2 to 10 exabytes per year in the next decade, and for genomics, projected somewhere from 2 to 40 exabytes a year. And the CPU power is completely beyond the projections of technology. For us, we now use like 1 billion CPU hours. We foresee using perhaps 200 billion CPU hours, and the number which is generated for genomics is 10 to the 16 CPU hours, something for which there exists no technology. Okay, so all of this points towards the need for a next-generation network integrated system. A major theme, which people have mentioned as an acronym, SDN, many times at this meeting, a major theme in both academia and industry is towards software-defined networking, replacing specialized, specific-purpose, so-called stovepipe hardware solutions with open-source software solutions, providing virtualized service that can coordinate and allocate resources and also allow you to create new architectures which are never envisaged before, essentially by separating the so-called data plane from the control plane. So controlling the network functions can be software-driven, and that can be separated from the actual switching infrastructure itself. And so here on the right, I made a cartoon of how it could work, and what I've tried to emphasize is that in building such an intelligent system, pervasive monitoring at all levels is required. Now, as a prerequisite to this, we've been working, along with many, using dynamic circuits. The use of dynamic circuits was pioneered by ESnet with our Oscar software, and now it's transitioned to this emerging standard called NSI. And we have used such dynamic circuits to allocate bandwidth and written agents that are able to couple some of our major applications for data transfers and for the disposition of hundreds of thousands of output files from all these analysis jobs around the world to dynamic circuits. We've done it over particular paths in the so-called LHC-OPN, but also across LHC1, across that complicated virtual routing and forwarding packet fabric. Well, so the agent requests a circuit, and if it succeeds, then we reconfigure the host and direct the traffic onto the circuit, so you have a bandwidth allocation. And as I mentioned, we've done this for across LHC1, but also have done exercises preparing for LSST in the future, and that's shown here, where you can see 5 dynamic paths created in this exercise. This is from April 2014, between Caltech, Michigan, Sao Paulo, also the national network in Brazil, and through AmLight, is shown on the map. And our monitoring system is monitoring all the agents and the operations. This is about our monitoring system, which is fairly unique. It is a worldwide agent-based system with a mean time between failure, which is hard to measure. We know it's greater than 7 years. And it's running at 370 sites. It's able of monitoring a huge number of parameters at 120 kilohertz, and has been tested that it can actually acquire parameters up to 1 megahertz around the world. There are these extra D servers. I showed you that traffic for any data, anytime, anywhere, and it's monitoring all those services, all those servers, as well as 100 wide area network links and some tens of thousands of computers, and has served about a couple of trillion of parameter values now. So we created a microcosm of this future system at Supercomputing 15, building on work which we did in previous years. And this shows the configuration with a ring at SC15 in Austin, and connecting to the Pacific Research Platform, which is a very important partner in this, along with AmLight and onward links to Brazil, to Michigan, Starlight, and then from there onward to Amsterdam and CERN. The whole point was to use our software-defined network developments to steer flows, to load balance, to orchestrate with sites. I'll show you a little bit more about that. And to scale up to the terabit per second network range, foreseeing what will be required in the coming years. Because the growth of traffic, which I showed you, is not really compatible with the growth of networks, the available infrastructures, a high-level concept is to have consistent operations, not only to enable the program to use networks effectively, but also to limit what we do, to use policy to prioritize different tasks, but also to install sort of high watermarks so that we remain friendly customers of the world's networks. At the same time, we're driving from the other end, so we're developing data transfer nodes capable of multiples of 100 gigabits per second. So this was the first thing about the scale. In the months before last November, the first 100 gig network interfaces had appeared, and two vendors, Mellanox and QLogic, gave us 29 of them. So we built data transfer servers with the help of Dell, Supermicro, and others, two that were capable of 400 gigabits a second and two 300. And we got single port flows of up to 170 gigabits a second or 120 gigabits a second over the wide area network on 100 gigabit link, but in both directions. And this is an application which was actually written by us in 2006, originally to show that you could do 1 gigabit a second flows, and it seems to be extremely scalable. Well, so there are technology drivers. 100 gigabit network cards appeared, servers capable of n times that, top-of-rack switches with using this Broadcom chip, which is 32 by 100 gig. The business for this year and onward is to match the new generation of solid-state disk to it, and there are other key milestones, such as the emergence of Intel's 3D cross-point memory, SSDs that can each do several gigabytes a second, and new interconnects. Okay, so this shows the configuration at SC15, a ring among several booths between Caltech, Michigan, Starlight booth, and also Dell and another company, EchoStreams, had a booth, and dark fibers to booths from Vanderbilt, Stanford, and others, and some of our partners. See the long list of partners. So also going out over multiple 100 gigabit links. And this shows some of the automatic topology discovery and connected to the ability to steer flows, which was used during this exercise. What we've been doing recently is to integrate end-to-end connections, and we've started to use what's called Open vSwitch, which is a very powerful software which is included in the standard Linux releases that allows you to exert quality of service and exert policy at the edges. It works in a protocol-independent way. It's very impressive what it does. I'll show you in a second. You can also limit flows, which is part of the picture now, as we increase capability to also have what we do be consistent with the operation of networks. And so we can control, as you'll see, traffic flow at any level.
We're at 30 minutes.
What's that?
We're about 30 minutes.
Okay, I'm coming to the end. So this shows some of the results. You can see the rates. We can set policy pretty much at any level from 1 to the full 100 gigabit per second. And on the right, the CPU utilization, about 16% of one core for the full flow. An interesting thing is that by exerting policy, the CPU penalty is only about 1%. And now we're extending it to a sort of multi-site concept. We're using Open vSwitch and circuits and also some of our SDN control of flows. We can also map policy onto multiple flows across multiple sites and coordinate things from end to end. Finally, I just wanted to mention the use of exascale systems. This is a concept that arose in the last year or so. Projecting forward, we see that our CPU needs will otherwise not be affordable. So by engaging and modifying our codes and using such systems, we see that this is the path to a solution. There are also long-term benefits, not only for our field, but for others, showing the way about how such systems can be used for data-intensive applications, making them part of this sort of global ecosystem for data-intensive sciences. It will help us build what's called a modern coding workforce, because such systems have a different architecture from what we're used to and the one which is really the way of the future. And we also hope to somewhat shape the future architecture of these systems to be more compatible with a wide range of applications by engaging with these facilities, for example, at Argonne in particular, and also with major manufacturers, starting with Intel, who are building and shaping these systems. So this is just a bit about the concept. Namely, we will have an exabyte and then more stored. And so the concept is to bring a so-called chunk of data from the high-energy physics laboratories and the Tier 2 sites, such as Caltech and others, to these facilities. Because of security concerns, a limited number of very high-performance data transfer nodes with proxies will be at the edge. The site can focus its security efforts on these limited number of proxies, and that will satisfy both the security concerns and the technical concerns. And what we will do with this, and what we're already starting to exercise, is bring these chunks over 100 gig, then 400 gig, then 1 terabit a second networks by the time the true exascale systems appear. And finally, before concluding, let me just mention that when we put all these mechanisms in place for all these use cases, that we also will apply machine learning. We're applying deep learning to our data analysis already, and here we'll apply them to the distributed global systems which are operating to support our data analysis, distribution, and access. Okay, so that's it. So the first run of the LHC brought us already a centennial discovery, the Higgs boson. The second run, which we're in the midst of, will, we hope, bring us even greater discoveries of physics beyond the standard model. Advanced networks have and will continue to be a key to the discoveries, not only in our field, but we know in other fields of data-intensive science. There are a diverse range of challenges to be faced and ones we're engaging with in scale, complexity, and the global scope of this problem. New approaches are being developed of software-defined networks that allow us to control such systems and data flows across them in a way that couldn't be done before, and also engaging with the emergence of exascale systems to bring them into the ecosystem of what we do. We think that if we succeed, which we expect to do, this will be important not only for our science, but for many other fields. And thinking to the future, and the future picture, for example, of the Internet of Things with millions of sources and sinks, this is perhaps the leading edge of how we'll deal with that. And by doing that, this will help shape not only research, but also many aspects of daily life.
Do we have some questions for Harvey? And if you do, please wait for the mic. Is there over here? No? Right over there.
Hi, thank you. Can you discuss at all if you have any ideas of how quantum computing or quantum networking may come into play in the future with you guys?
Yes. So the first thing to say about quantum computing is whenever you ask experts, such as my colleague at Caltech, how far is it away, the answer is always the same, 25 years. Okay, but moving beyond that, there are, in the farther future, quantum computing will certainly be able to solve certain classes of problems. Not all of these problems, but certain things like pattern recognition problems, security problems will also have a role. And I was privileged to have one of my colleagues whom I worked closely with had a student who worked for the D-Wave. And so we actually have made the first forays into quantum computing. And amazingly enough, when he reproduced his analysis in a different way on the quantum computing, he got similar results, not nonsense. So that's sort of where we are with quantum computing. It is becoming useful for certain applications. We have a few decades to go.
Anything else? Okay, I'm going to ask John Delaney to come on up then.
Well, I feel a little bit like the ambassador from oceanography. Which is, by comparison to what Harvey was discussing, is a third world science. And I'll try to, we've just stuck our toe gently into the 21st century, so I'd like to share that momentary bath with you. And also bring out the beautiful richness of the relationship between human beings and the oceans. We tend to take them for granted. A lot of people know that they're there. There's this great comment by a humorist, Dave Barry, who said, if all you've ever done is go to the ocean and just look at the surface, you've missed the entire point. It's a little bit like going to the circus and not going inside the tent, because everything is going on under the surface, and a huge amount of activity is going on under the surface, which functions over the past 4.5 billion years on this planet as the life support system for virtually all of us. We are as dependent upon what operates within the ocean as ecosystem services for the planet as the astronauts were when they were bouncing around on the moon hitting golf balls into outer space. If their backpacks went down, they were in real trouble. If the ocean fundamentally shifts, which it has done during geologic time, whatever the population is at 7.5 to 9 billion on the planet, there will be very serious consequences. So the ocean, I would submit, is an interesting area to play in. And these are, in case you need to catch a nap, let me just give you the talk in 30 seconds. Oceans essential to life on the continents, absolutely essential. If you don't now know about El Nino, you probably live in another world, maybe it's a fourth world, I don't know, but El Nino controls, I should say, El Nino significantly influences the distribution of drought and rainfall all over the planet. So if California is having a bit of a dry spell, so to speak, guess one of the drivers is El Nino. We don't understand it really well, and that's important. The other point I want to make is the oceans are very complex. Complexity is one of those things that's really difficult to assess and certainly to quantify, especially from the outside. But I would submit that the complexity of the ocean is proportional to n factorial, where n is the number of interactive processes that are involved in the ocean, and that's something close to 100 plus. And they all interact with one another. So the complexity is really serious. There are sophisticated models that need data to become predictive. We have really excellent models that have been done by elegant computer folks, but they are like absolutely beautiful flowers compared to being something that we can actually use to predict what the future is. And that requires data. And we're now dealing with novel technologies applied to the oceans that can transform our perceptions of the oceans and also feed these models so that someday, I don't know when, we may get to the point where we can look seriously at the planet. When you start thinking about a system, you try to define it so that everybody that's involved in the process understands what you're talking about. And this is our challenge, to optimize the benefits and to mitigate the risks of living on a planet that's really driven by only two fundamental energy sources. The first is one that we don't see much in Seattle, but it actually drives much of the processes that are there in the lower left, and you're all familiar with this. You're all aware of it. The photosynthesis and carbon cycling are a big deal. All the others are a big deal, especially if you are a farmer and you're subjected to drought or flooding. The other energy source is basically internal energy, and it drives plate tectonics, it drives volcanoes, it builds mountains, it moves the continents around. It's really very powerful. It's just quiet until it's not. A magnitude 9 earthquake is not quiet. It's a serious event. We will have one in the Northeast Pacific sometime in the next 100 years, most likely. And then, lately, since the Industrial Revolution, there's been a significant amount of activity done, imposed on the Earth by humans, and you're all aware of this story. I won't go into much detail, but to redirect the threats to the ocean, we have to begin to understand much more deeply the organization and the structure of marine ecosystems. What's one look like? Well, here's the message about complexity. I'm showing probably 10% of the, let's see, were we going to darken the room even further than this? Oh, really? We all have different perceptions. So the complexity is captured here, and this is the upper part, largely driven by the sun, and the lower part, largely driven by internal energy. And the ocean is the sandwich, or actually probably the bologna, between these two slices of very dynamic bread that's actually absorbing the input and has been ever since the planet developed an ocean. And the most significant event in that entire process was the evolution of life, probably. Some would argue that. But for about 3.8 to 4 billion years, life, the ocean, and those two energy sources have been interacting with one another, mostly in the ocean. So I love this quote by Marcel Proust, the real voyage of discovery consists not in seeking new landscapes, but in having new eyes. And to some extent what Harvey was talking about represents having new eyes to find something like the Higgs boson. At a much simpler level, we need eyes and optic nerves, I suppose, into the ocean, which we are not well suited to explore as land-based humans walking around on our hind legs. But tomorrow, the technologies that are evolving today, funded largely outside of the world of oceanography, are applicable to the oceans only if we have a very high bandwidth communication within the oceans. Standard oceanographic processes have been studied by ships and satellites which don't go very deep, don't penetrate the ocean very deeply. The odd mooring, but basically you cannot jam very much electromagnetic power or information through the ocean. It absorbs very significantly. So if we have an interesting way of developing these different kinds of technologies and attaching them to the capability of being in the ocean with high bandwidth, then we have something to really talk about. And I've summarized them here. I won't go through them all because most of you probably know something about some of them. Maybe some of you know a lot about all of them. But the key one at the bottom there is fiber optics. And we now lay fiber optic cables all over the planet. If you ever search on submarine fiber optic cables, you'll get a picture of the sea floor all over the world, and it's astounding how many hundreds and hundreds of thousands of kilometers fiber optic cable is there. And only lately has a couple thousand kilometers of cable been laid into the ocean for the purpose of conducting science in the ocean. That's what I'll talk about. And that's what this diagram is. So all these technologies that are coming online rapidly, probably each on their own Moore's Law curve, can all be combined into a system where we have the capability to be there offshore without having to be there. Not only that, this orange line is the, sounds like the DC Metro. The orange line is basically a first approach. We worked with the Canadians for quite a long while. They have a loop up to the north of the tectonic plate, and we have the one to the south, paid for by, I might add, taxes collected from every single one of you. So this actually belongs to you, and I'm hoping that you will use it in the way that pleases you and your children and your grandchildren. Let me talk a little bit about that. Here's the overview of what the Northeast Pacific looks like. It is the best outfitted portion of the planetary ocean that we currently have, with many tens of gigabit transmission per second transmission available to us. And Larry, don't worry about the pictures. I'll give you the slides. Who in the audience has ever refused Larry Smar their slides? He's a multiplying factor. But this is the bottom line. The real message, if I had only one slide to show, is this one: delivering unprecedented electrical power and communications bandwidth into the entire ocean volume will dramatically accelerate rates of technological adaptation as well as innovation, and it will attract a wide variety of youthful folks who, you know, there's got to be a few people that are not going to find the next boson, and you know, we'd love to have them come over to oceanography. We need the brain power. So here is, let me just take, I'm going to focus on my own specialty just because I could, you know, there's lots of topics here. I wanted to talk to you about this and show you, this is the mid-ocean ridge. It's spreading at about anywhere from 2 to 16 centimeters a year, pulling apart like the strings on, you know, at the speed your fingernails grow, and it runs around the world like the strings on a baseball. And here off the Pacific Northwest coast is the Juan de Fuca tectonic plate and the Juan de Fuca spreading center, and we're homing in on something called axial seamount. And that is axial seamount. Now that little box in the middle is a caldera. It's a volcanic depression. It's about 3 kilometers wide and about 7 kilometers long. And I will spend a bit of time talking with you about that. It's at the intersection of the Juan de Fuca tectonic plate and the Pacific plate. And it is wired, and it is restless. Again, it sounds like California. So the axial volcanoes in the inset there, you can see the orange box up near the caldera on top, and you can see another orange box down at the bottom, and they're all connected across the tectonic plate. There's a lot more to the story over in the subduction zone, just near Pacific City, but the system comes ashore in Pacific City and is hardwired, actually goes to the east as well as going to the south. And one of the things having to do with volcanoes, and this could, you know, right in your own special interest, if you're interested in fish stock migration patterns, you could configure for that. I happen to be passionate about underwater volcanoes for some reason. And when they erupt, they cause large plumes to be injected into the overlying water. And these plumes can be 20, 30, 40 kilometers across, and they spin up like a discus and then go wandering off in some direction, and we've never been able to track what they are. But most important, they carry novel microbes from subsurface that many biotech outfits are interested in, as well as pharmaceutical groups. So we think the origin of life on the planet may have actually started in these kinds of submarine volcanoes. But here's the caldera. You can see the edge of it on the left there. You can see the cable that comes into that little red box that I pointed to on 2 slides before is PN3B. And PN3B has about 7 or 8 cables that are anywhere from 1 kilometer to 4 kilometers long, stretching across the floor of the caldera. And the volcano, for the last 5 years, had been expanding and expanding and expanding. The seafloor under the caldera here had been rising at about 15 centimeters a year for a while, and then about 2.5, 3 years ago, it started to rise at 60 centimeters a year. So imagine in your own home, if your basement began to rise about that fast on a regular basis, you'd begin to get worried. Fortunately, nobody lives out here. But I want to take you into, there we are. I want to take you into that location right there. It's right at the edge of the caldera wall, and it is where we will have this next view. This is an underwater camera. You can see the camera here, the orange thing on the right, and it is viewing the mound. It's called Mushroom. The mound, it's about 5 meters tall, and you can see the hydrothermal fluid is rising past this little black chimney here, which will grow and fall and grow and fall and grow and fall. They're like the weeds of the seafloor hydrothermal systems. And to get a better overview, here's what the entire system looks like. You've got a much larger, broader view here. And this is all HD video, and it's all streaming at 14 minutes every 3 hours, day and night. And you can log into that directly if you wish. And here is the website. The general website, the data portal for OOI is in red, but the one that you want to go to right away, especially with your kids, is in blue. And we did that yesterday, and sadly, the transmission was at 8 o'clock this morning, and it's at 11 o'clock this morning. So if you can log into this, you will watch in real time 400 kilometers away, a camera turn on, the lights turn on, and you're seeing basically what I just showed you. I apologize for not being able to go all the way there, but let me just do something that is possibly interesting. Oh, what a shame. We tested this before the effort. Maybe I can bypass.
Wi-Fi on.
Let's see if this works. I don't want to tie up too much of your time. Tim, what did we not do?
Is the network still plugged in?
Yeah, it looks like it. I don't want to take up more time. We're not exactly on time right now. So. Oh yeah. Well, I've got another 55 slides.
We're not that okay.
I remember I turned the Wi-Fi on.
Right.
So we can just go with Wi-Fi if you like. Why don't we just do that?
Sure.
You know, you would think if you can wire the damn seafloor, you can actually. How did I know that you were going to say that, Larry? I had to get to it before you. Oh, geez. This is not what I intended. My apologies. Well, let me just go on and. All right.
The wire is plugged in.
I have no idea what my password is.
I can log in as myself.
Why don't you do that?
Yeah.
We rehearsed this last night, and we rehearsed it this morning.
Which?
Yeah.
Oh, it was loose. The wire was loose. Let's just see. I think it might be. No, it's not. Okay, I'll just log in.
Okay, so let me just I'll use poetry here to fill this in. One of the things that we face, and I think all of us share this view, finding that life, it may have originated on the seafloor, harkens back to the wonderful poetry by T.S. Eliot, who said in Little Gidding, said, "We shall not cease from exploration, and the end of all our exploring will be to arrive where we started and know the place for the first time. Arrive to the unknown, remembered gate where the last of earth left to discover is that which was the beginning. At the source of the longest river, the ocean, the voice of a hidden waterfall, the black smoker, not known because not looked for, but heard, half heard, in the stillness beneath the waves of the sea." How T.S. Eliot knew about the Cable Observatory and OOI, I do not know. What are we doing?
Internet's working. Open your link again.
Okay. In honor of Larry, we called this page Nove. He is a star in my book. One of many, I guess. He's definitely a star. So this is what the page looks like that you would get your transmission on, and it's dark now, but it's feeding out. You can see it's 59 minutes to the next display from 400 kilometers offshore. But here's something else I wanted to show you. If I click on this image, this has been assembled from the data that we brought ashore, and we've put together a huge image. So you can play with this. The more you click on it, the closer you get. And you can also see, I don't know how many of you can see this little red box in the lower right-hand corner. We go in, higher and higher resolution, and we still haven't used up that's only 50% of the pixels that we're looking at. So that's about as close as you can get while you're still getting pixels. Now, that is, of the original structure, that's this tiny little red box. So you have this entire thing in that kind of resolution 3 times a day. I'm sorry, every 3 hours for 14 minutes. So if you want to play with it, play with it. I mean, I think it's perfect for Cenic. With this type of thing, Louis, you and I should go on a trip together. All right. So back to the prepared talk. One thing we did, which was a big kick, was I had a workshop in Seattle. You can see the red box there. I had a workshop in Seattle in April 20 to 22, and we brought 90 people to Seattle to talk about, well, axial seamount is wired, and it's restless as hell. It's rising 60 centimeters a year. What's going to happen when it erupts? And everybody got home about a day and a half later, and the volcano erupted. So it was kind of, the planning was really bad. I think we should have worked more closely with your crew to run that conference. But here's what the earthquake patterns look like. I mean, whoops. That's not what I wanted to do. Here is the William Wilcock, one of my colleagues, put this together. And I'm running you through the eruption. Right there is the eruption. That's only a 2.5 day period when all those earthquakes took place. And all of the earthquakes are ones and twos. So they would not be picked up if you had land-based systems. And then here is what happened to the seafloor. You're looking at that in the center of the caldera. You can see that little red circle. There's a tilt meter that's measuring tilt and pressure, and the sea level, or the depth of the sea floor in this figure is the blue line in the upper left before the eruption, and the blue line in the lower right after the eruption, and it's about a 2.5 meter drop in about 12 hours. So this is an active volcano. And we have, for the first time ever, remotely, with no one in place at all, we have tracked what's going on. This is what we heard after the eruption. Sorry, after the earthquake. These are not earthquakes. These are something else. We didn't know what they were. These are explosions of some sort, and they're waterborne acoustic signals, not seismic signals coming through the seafloor. So I won't beat you to death with that, but probably it can be sold through. Yeah, my ringtone. Okay, so to get out of this, I have to do that. And this, I just wanted to show you. We then began plotting where those explosions were coming from. And here is what that looks like. So the slider at the bottom is going right through the eruption. Those are all the blue locations there are all the earthquakes. But the explosions are the red ones. And they were 16 kilometers north of the caldera where we thought all the action was. So we go north. We couldn't get out there for about 6 months, or about 3.5 months. But when we went north, we mapped the area where the earthquakes or the explosions had been. And lo and behold, there was a lava flow. You can see it outlined here in the upper right. The lava flow had grown in about a month. It had grown to about 2/3 the height of the Space Needle in Seattle. And it's about 7 kilometers across. So this is something we had never seen before. It must happen all the time. We just hadn't seen it. So in the future, here's what I would like to see us do, working, of course, with Lewis and his fundraising group. We would like to instrument the entire volcano in many, many new and different ways. And we would like to have autonomous vehicles moving back and forth in sort of a standard milk run, so we know what the system looks like before it erupts. And this is called an AUV, an autonomous underwater vehicle, and we think that we should be able to do this very routinely for almost a pittance, a couple million. And this is what we expect. Again, Mark Stormer steps in with his capacity to visualize the wild dreams of John Delaney. And this is what we imagine is going to happen. And then the mobile platforms, you can barely see them. They're tiny little things. Will start flying. Here's one right here. It's going to fly through that plume. And there's another one up here. See it flying through the plume. In doing so, for the first time ever, we start to quantify one of the most powerful forces on the planet, which is underwater volcanism. Why is that interesting to you? It may not be, but it sure is cool. And and here is another. This is, I call this Imagineering. happen. All right, so this is, you heard yesterday from Mary Miller about this thing, so I'm not going to repeat it, but this is stunningly breakthrough science. We will be able to do we can now do remote genomic analyses offshore with nobody in sight. It's doable. It's being done by folks at Monterey Bay Aquarium. Here's something else. You find something that's happening offshore. We detected an earthquake. We now know how to recognize them. As soon as we recognize them, we would deploy the robotic troops into the area, and they would fly into axial seamount. That's what you're looking at there. They would fly directly into the erupting plume. They would take samples, and they would eject the samples on a flotation device to the surface. And guess what? There's some leftover drones in the United States. We fly in, pick up the drones, and bring 36 hours after the eruption, we bring the microbes that have never been to the surface of the planet before back for research in laboratories of different places, possibly Seattle. So what's new about this? Well, those are ideas. Here is what's really probably the most important thing, is these cables are only in one place at one time. And I get a lot of static from my colleagues saying, well, it's not like a ship. You can't go anywhere you want. But they're there all the time. They're sending data all the time. You can send data back in this case, you can do 10 different kinds of science simultaneously over the entire volume, and you can have it connected hardwired to the internet, so anybody anywhere on the planet, once Larry and his colleagues get through, we will be able to basically bring the ocean to the public. We will never bring all the public to the ocean, that's for sure. These are the number of places around, at least the northern hemisphere, where people are looking. The red dots are cabled observatories that are coming, and the green ones are the ones that are in place. For working with Cenic, this is what we had in mind. And this could be any topic in the middle. I've chosen axial seamount, but we would have the ecology, the biology, the physics, geology, chemistry, hydrology, all that content in state data streams with visualizations done by Mark Stormer and his crowd, working with Lewis and his group. And the displays would be made available across the internet to anyone who is actually interested. This is the kind of management structure we would need, and there is a beginning of Ocean Commons, but wouldn't it be cool? Here is an idea of what next generation discussions in a classroom might consist of. We're not there yet. But next time I give a talk here, Lewis, what I really would like to do is have a holographic display in the middle of the room, everybody in the theater and around here, and we actually are looking at holography from the deep ocean. Now, I don't see any reason why you couldn't have that ready 5 years from now. I mean, what a way to capture, well, I won't make a political comment, but capture people with science. I did make a political comment, didn't I? All right, so wrapping it up, this man really turns me on. I don't think you saw what he said. This is really cool. Sometimes I think we're alone in the universe, and sometimes I think we're not. Either way, it's quite staggering. And here is our nearest and best hope in the short term. The planet on the upper right is Europa. There's a wonderful story here. This is a picture of Io, the nearest planet, moon of Jupiter. And that's an eruption that's taking place on the limb of Io in real time when the Voyager flew by. And here is what we think Europa looks like. It's clear that it's got an ocean under the frozen surface. And we speculate, all of us speculate, what does it look like underneath? If there's oceans and there's volcanoes, did life get off the ground there? And is it something different? This is captivating in my view. So to end, I'd like to end with a poem by Basho. And this is just a lovely poem because what he does, I don't know if he was thinking this way, but he juxtaposes the complexity of the sea that we live with against the seeming tranquility of the Milky Way. But the truth of the matter is, everything we learn about studying the ocean here on this planet and finding life in exotic forms and exotic places in this ocean can be exportable to other planets when we go searching for life, or when our children set out to search for life under those conditions. So my fascination at this point, I was talking with Larry about this yesterday, would be to begin telling stories, and I'd love to use Cenic as a platform to do this, telling stories about the global ocean upon which everyone depends. And I would like it to be something like, who knows, this kind of story I just told you. But writ large, it could be many, many stories. And it could be presented in a way that anybody could have access to any aspect of it, you know, short 20-minute lectures, because that's the end of my talk. Thank you. We should probably go on. I think.
Do we have till 10:30 or 10:45? 10:45, okay, we can take a question. We can take like one or two questions for John. Yes, right up here. Oh, sorry.
So always a great talk to hear, John. So some people in the room might not know that we have a similar, maybe not quite so fully developed underwater observation network in California. Could you describe that very quickly, the one in the Monterey Bay?
Oh, yes. Back in the early years, we decided that we would be foolish to put in a proposal for $150 million to build a cable over the Juan de Fuca Plate if we had not demonstrated that something comparable to that could be done. So there was about an $8 million proposal that went in from the Monterey Bay Aquarium Research Institute, supported by Marcia McNutt at the time, and with a lot of the folks there involved, and all the rest of us were involved in helping put it together. And NSF did indeed fund a single node cable that is just adjacent to the canyon, the Monterey Canyon, which is by the Salinas River, has scoured that out. And it's pretty interesting. It's not quite the same topology and wiring capability, but the capability is there, as is the one that the Canadians have. So it's pretty cool. And what the problem is, as I see it, is that people are not used to this capability. There are entire communities of astronomers, there are entire communities of physicists. They've been around long before Galileo, you know, but in oceanography, to do real-time science using a fiber optic cable, it's kind of a new idea, and it's going to take a little bit of time to catch on. That is why, for me, Cenic is so important, because it's with Cenic we get to the public, just the way NASA gets to the public with outer space. There's, for reasons I cannot fathom, and bad pun, the public is as more captivated by outer space than they are inner space, and yet we are much more dependent on the behavior and the ecosystem services, to use a clumsy term, of the global ocean.
Got one more over here.
I'm not in the oceanography business, but I was wondering, have you worked with Thomas Ballard? And what
Bob.
about a TED Talk?
Is Thomas Bob's brother? You mean Bob Ballard? Yeah, you do.
You do.
But thank you for the question. Let the record show that it's Bob. Because, I mean, he could watch these proceedings, right? And then, oh my, if he ever found out who you were. Bob Ballard is one, you know, we stand on the shoulders of giants, and Bob is one of the people that moved into the ocean in novel and new ways years ago, when he advocated that we not all stay inside the submersible, that we use remotely operated vehicles, and that is, in fact, the new wave of oceanography. So yeah, Bob's a wonderful educator, explorer, There are people like me who even think he's a scientist, but some of my colleagues.
Yeah, thanks. Great, John. Do you anticipate, as you add more autonomous vehicles and instrumentation that isn't sitting down on the floor, that there'd be more issues with incursion by fisheries and shipping?
That's a really good question. We went way out of our way when we laid the cable. We went to all the coastal communities that were nearby. We talked to the fishermen. We talked to the cable laying folks. I mean, you have to get permission to lay cables over somebody else's cable. And the fishermen, we went to the schools and talked to the kids of the fishermen and said, you know, one of the things this is going to let us know is on the Oregon coast when some of the big earthquakes are liable to come. And before long, the fishermen, yeah, well, we'll work with you, and we have worked that out. And so far, we have not had any incursions. Whether that goodwill will continue, I don't know. For sure, the fishermen, the Cable Observatory in Canada has, part of the system has been knocked over and pulled out by a fishing trawler that they never caught. So, but, you know, we did a lot of homework, and we anticipate that there'll be encounters, as there are now for the cable industry. We can't afford, however, we don't have the funding of the cable industry. The cable industry has a hotline. If you feel like your fishing vessel is caught on something on the seafloor, you can call, and they will say, cut your rig and we'll replace it for only $250,000. NSF didn't really want to buy into that.
Okay, last question.
Hi, Eli Dart from ESnet. There's a fabulous, fabulous talk, really inspiring. So I think I speak for several people in this room. I'm a technologist, not a scientist, unfortunately.
Well, thank God for you, because I'm a scientist. You know, I took screwdrivers when I was in college, but I never really mastered technology.
We all play to our strengths, I hope. What I would very much like to do is I want to understand what people like, in concrete terms, what can people like me do to make people like you more productive, right? I mean, so this is amazing stuff that you're doing, and there are a lot of us who would really much rather be working on enabling your work than you know, optimizing click-through rates on Pinterest or, you know, whatever, right? I am totally serious. I am totally serious. Right? So,
Well,
how do we do this?
All right, for a moment, I'm going to become Larry Smarr. Well, thank you very much for that, and I really think that if you send money, I'll be happy. But John Delaney says, spread the word. You know, get kids involved. We're not talking about small-time stuff here. We're talking about the future of the planet. We're talking about the system that keeps us all alive. So spread the word. You know, put it into the hands of people in your neighborhood. I'm happy to share through Lewis, if you like, all these slides. You can use the damn things and go to your local Boy Scout troop or church group or whatever and just talk about it. You know, we're starting at square one here. It's early times yet. So meet me afterwards by the coffee pot, and I'll get your name and we'll get some slides to you. Any one of you now could give a 10-minute talk on what I just did. You know, it's easy.
Thank you. I also have a note from the back here that the graphics on the recorded video are just amazing. So if you want to look at that afterwards, you can take a look.
Also, just amazing was the pair of talks I heard. Beautiful, beautiful talks, imagination-stretching talks, and it's an honor to be on this panel, so thank you to my colleagues. My talk will be a little bit different. In some sense, it's in the spirit of Eli's question. So it's going to be an argument about how networks, how our organizations, and campuses too, can organize themselves to promote the best interests of scientific communities and to respond to the challenges that have been outlined here, and to the sometimes, you know, baffling set of challenges, to respond to them over the next decade. I'll begin by confessing I was a little bit puzzled about what logos to put on this title slide. So I was very happy to have been invited to be a Cenic board member, so the Cenic logo is a clear one to use. And I am the most recent former ESnet director in the world. ESnet is now being very ably and expertly led by Inder Manga on an acting basis, and there's a global search underway for a new ESnet director. But I think the statute of limitations on my using the ESnet logo goes for another week or two. And a lot of these observations are essentially a distillation of thoughts I've had in the last 5 years running ESnet. Harvey showed this map, but for those who don't know, the Energy Sciences Network, the organization that I just recently ran, is the mission network for the Department of Energy. And the Department of Energy conducts a lot of the basic science research in the physical science in the United States. It's not as well known as the National Institutes for Health or the National Science Foundation, but it manages the National Laboratory Complex in the US and several dozen large-scale scientific instruments and participates in many large-scale global scientific collaborations. And so DOE is an important player, and ESnet interconnects the DOE complex. This is perfectly clear from Harvey's talk, but I want to underline the fact that for the last 3 decades or so, there's been a very deep connection between data-intensive science and networking. And in particular, the physics community has really pushed on the boundary of the networking community over and over, and in many cases really led the way for the networking community. And Harvey personally has played an important role in that. And I like to show this slide because it's a picture of the workshop report in 1986, so 3 decades ago, before the commercialization of the internet, that led to the creation of the Energy Sciences Network. And it was a fusion scientists and physicists coming together and giving their requirements at the workshop. And the 2 simple things they asked for coming out of the workshop can really be summarized very briefly. The first is that the scientists wanted local area networks to work about the same way as wide area networks. They thought it really shouldn't matter whether you're exchanging data locally or around the world. And the second is a plea for a kind of virtualization service. They were used to using Unix time-sharing machines. They kind of liked that model. And they simply asked if a network could behave the same way. Could they experience the network as if they were the only tenants on the network and not sharing capacity with lots of others? And really, for the last 30 years, the advanced R&E networking community has been trying to deliver on these requests and hasn't actually done so yet. And I think in some ways the research program of ESnet and other research networks around the country can be summarized as attempts to finally do this work for the physicists. So I'm going to make an argument about what we might be doing productively in the future, but I want to first sum up some of the major trends happening in research networking. Some of these you heard in the 2 talks, and maybe some of them not so much, but it helps give sort of introduction for the argument I'm going to make. And the first is really the relentless growth in traffic that the research and education networks are seeing. These graphs, it used to be if someone wanted to see the latest graph of traffic for ESnet, they would send me a note and I would almost always send back the latest graph I had. But now these graphs are available online at my.es.net. The URL is right down here. And these are so up to the month, up to date every month. And the top graph shows linear. It's a linear graph of traffic accepted by ESnet every month since the early 1990s. And the bottom graph is the same data on an exponential scale. So the bottom graph shows you very clearly that we're on roughly a Moore's law growth curve, and it's been roughly steady, as Harvey said, for the last 30 years. And the top graph gives you a kind of emotional appreciation of what that means. And in particular, that uptick in the last several months is the kind of thing that makes network engineers and those who fund them really, kind of blink and swallow hard. And it's very challenging to engineer for exponential traffic growth with linear budgets, but that is one of our core challenges. This last uptick has been largely the result of LHC Run 2 traffic, so the kind of traffic that Harvey was describing. And in fact, the amount of traffic carried on Cenic and ESnet, I just verified this last week, is almost identical, so roughly about 40 petabytes a month. The traffic mixes are a little different, the use cases are a little bit different, but both of us carry a large number of elephant flows, large, long-lived, high throughput flows for data transfer, and the same is true of Internet 2 as well. Now, the other thing that's important to say is that the diversity of traffic sources is also growing relentlessly. It used to be the case that these flows came from a small number of large instruments, and now they're coming from all over the place, and they're even coming from the deep ocean floor. And this is a really profound change. It means we need to engineer systems that are automated, responsive, and flexible to accommodate these flows in real time. We can't anticipate 2 and 5 years into the future where the workflows and the flows will be. We have to build systems that can detect these automatically and respond to the needs in real time. A second fact, the first fact about traffic growth is a little obvious. This is somewhat non-obvious, and this is that all research networks, Cenic, Internet2, SurfNet, Géant, DFN, ESnet, we all share fate. And in a sense, that makes us very different from high-performance computing centers, and it makes us very different from commercial networks. In a sense, it doesn't matter how good Cenic is, or ESnet is, or Internet2 is in isolation. Because, for instance, 80% of ESnet traffic leaves the DOE complex and travels to other networks, Cenic, Internet2, and the others that I mentioned. And just in the last week, I've tried to get the same numbers for a European network and for Cenic, and I think it's roughly similar. Maybe the differences are plus or minus 10% or so. So the only thing that matters is really the end-to-end solution that scientists like John and Harvey receive. Their science is not constrained to regional or national boundaries, and so our network services can't be either. And it also has this really important implication. Any optimization you make, any tool you build, any service you build, if it's for your own network only, that's nice. But if it can't scale globally, and I mean scale technically, scale culturally, scale in terms of its attractiveness, then it's sort of wasted effort. And we really, really share fate. We really, really need to work together and work globally. There's also what I describe as the mantle of responsibility that is increasingly following on global research organizations. And you can see this, in other words, major scientific, multi-billion-dollar scientific instruments around the world depend fundamentally on our networks to get their work done. And you can see this very plainly in the evolution of the LHC data model that Harvey was describing. At first, it had a somewhat, I wouldn't say pessimistic, but cautious view towards global networks. So it used networks to copy data, but data was copied in many places around the world, cautiously, maybe a tiny bit pessimistically. Very quickly, it was clear that the network systems engineered around the world to support the physicists were so good that you could relax that. Relax the copying regime into sort of an optimistic caching regime, and now it's really very interesting. Data is fetched just before it's needed at the block level sometimes. And so fundamentally, the importance of global networking has risen, and the faith entrusted in global networks has risen. And indeed, the relevance of geography has decreased. So that mantle responsibility is very clear. I think we all understand it in the case of high-energy physics, but it's now expanding to include many other domain sciences. In fact, it's really hard to imagine, at least in my knowledge, a large-scale scientific project or even a medium-scale project anywhere in the world that doesn't depend fundamentally on the performance of global R&E networks. International networks, national networks, regional networks, and local networks. Without those networks, all of these critically important scientific collaborations simply and literally grind to a halt. And some of these scientific fields, and I would point to climate especially, are manifestly slowed down at the moment because global mobility for their data sets isn't what it ought to be. And that's a shame. In the DOE complex, there is a paradigm arising that we call superfacility. I think it's being rebranded just in slightly different terms to be the convergence of HPC and data-intensive science. But the idea is that very short-lived collaborations might rise up around beam time that's available, say, at a DOE light source, and data might need to be computed in multiple places around the world and returned to the light source in real time in order for work to get done. In this case, important work to prototype the development of new kinds of photovoltaic cells that can be printed as if from an inkjet printer. We can't facilitate that kind of science without building nimble and responsive APIs and systems to enable this kind of workflow. It's just as simple as that. So the mantle of responsibility is heavy. On the positive side, I have seen a lot of evidence in the last couple of years of the rise of regional and global coordination around science engagement, around architecture, software, and now just at the beginning, I think, stage is cybersecurity. And I would probably point to the Pacific Research Platform. You've heard a lot about it already. Many of you are participants in it. I won't describe what it is, but I would point to it as maybe the most interesting and compelling instance of that. And we'll know that PRP was successful if in a few years everyone says, oh, that was an obvious idea, we were already doing that ourselves. And it becomes perfectly apparent that, of course, you would organize your science DMZs and you'd organize your science engagement activities beyond the campus scale. You'd organize regionally and beyond regionally, even nationally and internationally. But there's lots of other evidence of growing collaboration. You know, we're seeing many more workshops and BOFs on the topic of science engagement across organizations like the one coming up at TNC. Just a tiny example, the Personar project is now unforked. It used to be forked between US effort and European, and that's changed, and that's very good. Over time, the networks that we often depend on for services and for partnership, Level 3, Verizon, AT&T, and many other carriers are becoming quite different from research and education networks, and that's okay. But GEONT, Internet 2, ESnet, and Cenic have very different constituencies, but also different workflows, different data transfer patterns, different collaboration patterns, and different needs. Another reason we need to work together. So now, what does this mean for the next 10 years, briefly? I think when I came to ESnet, I needed a catchphrase, and my catchphrase was network as instrument. I wanted to move beyond thinking of networking as a black box, an infrastructure where bits went in and came out, and really to begin thinking about global networks as extensions of the discovery instruments that they serve. And I think in the next 10 years, that perspective is absolutely right and necessary, but not sufficient. And so I would like to move us all into a new mode of thinking. Networks must become instigators, instigators of change, really, to advance their mission. And so, an instrument is an important conceptual leap in thinking about networks, but it also could be seen as somewhat passive. An instigator is an active agent, and it influences its environment, and it reacts with other instigators. And I'm going to talk about very quickly 3 modes of instigation. There are many modes of instigation, but these are 3 that I know from ESnet. And at ESnet, we organize separate groups to do the instigation, so these modes became separate groups. One of them is the mode of science engagement, or you can say mission engagement if you're not thinking primarily about science. And this is the idea of creating a group of people like Eli Dart and his colleagues at ESnet whose work is to make science go faster by engaging directly with scientific communities. And it's not just technical work. It requires understanding workflows, the culture and sociology of science. It requires understanding funding streams. It's very interesting, complex, multidisciplinary work. These groups also need to understand the requirements of the communities they serve by eliciting them in a formal, methodical way, not just sort of saying, I talked to a physicist the other day and I think they need X, or not projecting their own love of technology onto scientific collaborations, but actually methodically learning what collaborations do, what they are, what they need, and documenting that. Promoting architectures for performance and flexibility, and I will just say that the PRP is in some sense a fruit of that kind of promotion on the part of Eli and others, and understanding science impacting bottlenecks wherever they are worldwide and getting on them and removing them so that science can go faster without thinking too much about whether they are in your domain or someone else's, but working collectively and globally on those topics, science engagement. The second, programmability. And I should have an asterisk here because as soon as I use that term, Michael Sinatra sighs a little bit. I've heard him a little bit. And it's true, it's not a great term to describe the shift in the way of what it means to network, but it's the best one I can come up with. It's not just about open flow. It's about the need to develop much more flexible service models, new APIs, and allow applications and scheduling middleware to pose complex questions of networks. For instance, is it faster to move the data between A and B or just recompute it? Questions like that, and also to express complex intentions, like I'd like to set up an LHC1-like overlay covering 40 nations. Please make that happen. That's going to take a lot of work. Connected with this work is also the development of open modules and modular tools that we can all use, and the reuse of other people's modular tools. And so we want to stamp out not invented here syndrome. For every tool that an organization, I think, develops and publicizes, they should try to use a dozen or so tools that peer networks have developed and publicized. All right, I'm just going to pass on to the next one. The gloss on this might be cybersecurity, but I like to recast this in terms of safety, because cybersecurity isn't maybe a goal that people can march behind, but the idea of a safe and open and secure internet that enables learning, teaching, and discovery is something I think we can all believe in. And so far, I would observe that the National Research and Education Networks and the regionals have been really, really lucky. Campus is not so lucky. The campuses have been hit by many sophisticated cybersecurity attacks, and their teams are working very hard to mitigate those. The NRINs so far have dodged a lot of bullets. When you think about what could happen to NRINs, there's some scenarios that are really bad. For instance, what about a ransomware scenario that locks up an entire regional or national network? Attacker says, I have your business continuity docs, I have your diagrams, I have your configurations, and I've wiped out your configs. Good luck recovering from that in a few days. So we need to really begin to build this concept of safety into our cultures as a foundational value. Without internet safety, there is no productive science in the U.S. It's as simple as that. I heard a lot about it in my role as a DOE and LBNL division director, but I think all networks are thinking about it at the moment. Every network is going to need to ask whether and how it provides security services. Networks have been used to thinking about security of the networks. They're going to need to start thinking about security on the network. That's a big, big transition. This cuts across all Cenic missions, all Internet 2 missions, all ESnet missions. There's beginnings of a collaboration here. I won't go into them, but there's certainly ESnet, Cenic, Internet 2 are working with peer organizations to collaborate on this topic. So summary, network as instigator, our role for the next 10 years, science engagement, programmability, safety of the internet. One implication, I think, is that we need to think a lot about our workforce. There's going to be new job categories required to meet these new and demanding roles that are being built. Cyber infrastructure engineers, many of your campuses have them. Many of them are advocating generously on behalf of CI engineering around the country, actually. And we can thank the National Science Foundation for funding this. There's going to need to be a lot more of those data scientists, people who think about network programming, not just networking, and security specialists who have truly holistic skills. We have not done enough thinking as a community about how to create a healthy pipeline of such professionals, and above all, a diverse pipeline. That's a whole other topic in itself, a panel, a conference in and of itself. But although I think we've done a little bit better on diversity in the last couple of years, we're still fundamentally failing. And we're failing on the pipeline question as well. So there's a lot of work that needs to be done on both of these questions. Last slide. I just want to remind everyone that networks don't matter very much, as I'm fond of reminding audiences. Networks serve people. People matter. Networks do something interesting for people. They make geography irrelevant, so they obviate geography. And that has certain implications that are profound. They're democratizing, and they make the things that we care about go better and faster. They remove friction. This is the vision statement for ESnet that I'm very fond of. Scientific progress will be unconstrained by the physical location of instruments, people, computational resources, or data. It doesn't matter where in the world those things are. It shouldn't matter. Progress will be completely unconstrained. But now that I'm affiliated with Cenic, I will say I'd like to think about the transferability of that mission statement. It really is very transferable. You can insert your mission, whether it's literacy or music education or any other number of topics, and you can insert the resources that you care about, libraries, schools, performance spaces, and the same thing is true. We, as networkers, need to instigate along the lines I mentioned in order to make this vision increasingly true for all of our constituencies in the next decade. Thanks. That's my talk.
We can take questions for Greg, or
maybe I'll sit so the whole panel.
maybe, yeah, let's just take questions for the whole panel. And please wait for a mic, and we have a hand up here. Who is that?
Larry Smarr. So for Harvey and Greg particularly, the speed at which the wide area networks are increasing is quite phenomenal. And so I guess the question is the implication for a world of distributed data and compute. And we hear a lot about data needs to be local to where the compute is, but local, really, if you mean like on a cluster or a supercomputer, the data can't get off the disk to the memories faster than the backplane of the cluster. And if your wide area networks are now terabit, they're faster than the cluster. So the data, wherever it is sort of at least as co-located with the processors, other than speed of light, as if it were local. So how do you see this issue of, does it matter where you know, the data and the compute are or not in this very high speed wide area network?
It does matter. Generation of wide area networks is still 7 to 8 years long. We're in the middle of the present 100 gig generation. You can see trials, including the first across oceans at 400 gig. There was a production 400 gig link done, well, there is a production network now done by ESnet, and there was a trial done a year or two ago by Alcatel and Orange. And IEEE now has a date, end of 2017, for the 400 gig Ethernet standard. So that's the time scale. But things are happening much more quickly in the architecture of servers. I mean, we had only weeks to put together these multiple 100 gig servers, and they're not very big. And that's also continuing. So also on motherboards, you mentioned the flow of data between the processors and storage, for example, and network interfaces. Computer manufacturers, Intel for one, is working very hard to overcome that. So I think the balance is different. I mean, we're quite serious about not only enabling our community, but working hard to remain compatible or friendly customers of the world's networks for those reasons.
And maybe I'd add to that, I think the only sensible approach a network can take is to be agnostic on this question, because again, in the life cycle of networks, 7 to 8 year life cycle, it just makes sense to plan for not only different collaborations to have different opinions, but for their opinions to change very rapidly over time. In fact, some of the data patterns, I was just at ACAT in Valparaiso actually, and heard a lot about, this is a intersection, it's a conference at the intersection of physics and computing, and heard a lot about future computational models for Atlas and CMS, and they were, is it going to be a cloud? Is it going to be Atlas at home? Is it going to be a continuation of the tiered system? I don't know. But I know ESnet and other research networks will need to accommodate profound changes in those workflows. It's a debate I often heard as a division director at LBNL, and it was advanced somewhat, I would think, a little bit ideologically on both sides, but really the right response is agnosticism. The data needs to be where it needs to be to get the science done.
I want to respond in a different way. If I could, I want to respond in an entirely different way. The first panel on closing the digital divide in California, there was a comment that whatever your solution has to be dynamic. I think that's fundamental, and it doesn't just apply to our science, but it also applies to research and education networks and their communities as a whole, and also to K-12. That if you come and say, look, I've solved your problem, I'll see you in 10 years, that's not a solution. That's freezing you in the past and making you non-competitive as a society.
Last question.
I'd like the panel to comment on real-time data and real-time data analysis. It obviously is very important for weather and earthquakes to know what's happening in real time, but what is the power of real time for sort of analyzing and computing LHC or the bottom of the ocean?
Our case is an easy one because the times are measured in minutes to hours and sometimes longer, but what you raise is a very, very important issue. We showed the sky surveys, both Larry and I, LSST as a leading edge project that brings in the real-time aspects. There are other examples which we didn't show. One is called weather nowcasting, which is extremely important, where you have real-time data with a great deal of resolution and geographical detail, and the point is to localize severe patterns. I mean, understanding where tornadoes are likely to happen, where they are happening, you know, with all the implications. Those are very important things which we didn't cover sufficiently perhaps in our talks.
Maybe I'd add, there's a direct connection between the promise and the challenges of real-time computation over data that's gathered in real time and networking. And so that model of dynamic networking that I described as super facility is just all about that. There's these instruments often funded by DOE, some by NSF, where you can't develop a new drug, or in many cases increasingly a new material for commercialization without passing through one of these instruments. They're X-ray or neutron light sources. And often the computation that's needed on that data needs to happen in real time in order to give feedback to the experimentalists. And often that computation needs to occur far away, maybe 2 different computers far away. So this is yet another, the promise of this style of science is great, but the demands it places on networking also great.
There are a number of processes that operate within the ocean that are transient and yet very, very powerful. And it would be a fundamental new way of studying the oceans in order to have real-time access to the onset of such phenomena and the capacity to, on the spur of the moment, redeploy assets that are hundreds of kilometers away into the area where the events are taking place. I think that alone, that as a service basically to the modeling communities who in fact could begin to get better and better and better at taking the limited amount of data we have. It's working on land at, the dangerous storms are an example, but the ocean is a very different world, and a lot of things go on in the ocean. Many people don't realize that although we tend to think of environmental threats, climate change, weather, coming from the atmosphere, the truth is there's less total heat tied up in the entire atmosphere than there is in the upper 2 meters of seawater. So the ocean is a gigantic engine that is basically buffering our system at one level, and yet, what happens when a gigantic engine begins to go the wrong direction? That's a problem. I think also the best advice to people who are living in, say, the Circum-Pacific, where they're threatened by magnitude 9 earthquakes or 8.5, 9 earthquakes, best advice, at least if you live near the shore, is if you feel a lot of heavy-duty shaking, run uphill. But there are a lot of people who don't have hills nearby, and that is a serious issue. The recent article in the New Yorker was a little bit over the top in a sense, where the woman said anything west of I-5 is toast at a magnitude 9 earthquake. That's probably not true. But what it pointed up, more importantly, is that we are vastly underprepared. Most of the buildings, even where we educate our kids, most of the places where people are going to encounter a magnitude 9 are not well prepared. And so that's not so much a direct answer to your question, Mary, but it is an interesting one. 2 more. One would be, I think we need sensors in the ocean that can actually survive magnitude 9 earthquakes and give you, minute by minute, the shape of the surface of the ocean, which is the tsunami. And if you match the shape of the surface of the ocean with the shape of the sea floor, which you should already have on record, then your models have the potential to actually predict the most destructive portions of where that's liable to come ashore versus, less destructive. Those kinds of things, I think, are doable. And finally, of course, tapping into the powerful philosophy of the exploratorium, I think if we can turn at least the study of the oceans into an interactive kind of phenomenon where children, young people, any retirees actually can interact with what's going on out there. This is a ways away. At first it seems lavish, but I don't see any particular reason why you couldn't make a lot of money if you had a couple really good groups who make games out of real-time data flow. And then you are faced with the idea of, oh, wow, this is really actually happening now. And there's a different character to that when kids realize that this is not, you know, this is not just a game, and I'll walk outdoors and do something else later. This is real-time science, and I think that's going to be captivating at levels it's hard for us really to imagine at this point.
We have all been so fortunate this morning to hear this erudite panel. Let's give them a big hand.